So my name is Harry Mason, and I have a pleasure of presenting a cool new acceleration technique to you all. Now, I am aware how broad a range this session is, and you may not all be familiar with acceleration, so not to worry. I'm starting simple. I'm going to define acceleration as producing images from an undersampled data set, just using less data than we really should to produce those images. It's an important second rule. You really want those images to look good. You don't want to be accelerating a lot, using the smallest amount of data you can unless you're producing good quality brains. And to help with that, I've got a little rule that's going to be a recurring theme throughout this talk. The more you know about how your data should look, the more information you have about the structures or where there's redundancy, the more you can accelerate. So why should you accelerate? Well, there's a few reasons. It does help with physiological noise, for instance, but the main reason for me is temporal degrees of freedom. The reason being is that gives you a lot of play. It's like money. You can spend it in lots of ways. You can increase the temporal resolution, which if you're doing multivariate analysis, will really increase your statistical power. Or you can play around with spatial resolution. You can get a better quality brain if you've got this extra degree of freedom. Now, when I say acceleration, this is probably one of the first methods you think about. It's simultaneous multi slice. It's a parallel imaging method. And again, I'm going back to this theme. The knowledge we have here is about the coil sensitivity maps. It means we can scan multiple lines at once and unalias them because we know about where they overlap. That's not what I'm talking about now. This is an example, because I'm going to talk about KT methods. Again, you can see the similarities here. It's a little bit outside a lot of your fields, I'm going to guess, but it's just an acceleration method. We're looking at where there's going to be redundancies. In this case, it's in the space-time data sets, in the spatial temporal structure. Here, though, we're going to reconstruct the entire set of FMRI at once, which means we're going to preserve the signals in a way which SMS sometimes doesn't. And this isn't competing against SMS as well. We can use the coil information together with it to produce high-quality images. OK, this is KT methods. I'm now going to introduce a certain type of KT method. This is KT faster. It was produced by Chu et al. And the spatial temporal structure we're abusing here is there's only a limited number of interesting networks in fMRI, far fewer than the amount of pixels, for instance. As such, you can represent this data with only a limited number of spatial patterns and temporal patterns. This means it's inherently low rank. And these domains, they align as well. The time information speeds into the space information. So they use a method called matrix completion. So you can either produce a very slow matrix. You've got these fully sampled scans in K-space over a very slow period in time. Or you can spread it out. You can distribute your samples, and you can use that information, that knowledge you have, that there's only low rank, to help reconstruct the missing information. This is just quickly some of the mathematics we use a data consistency term with a rank constraint. It's quite a simple optimization, but we're going to build off this. Now, when we're doing this, there's a particular type of trajectory we like to use, and that is turbine imaging. Oh, I'm afraid it's gone a bit fast. Turbine images are radial spokes of EPI which rotate, and they're never going to overlap. They're separated by something called the golden angle, which means we can produce however many we like at any time. So we can either get a large amount of spokes and produce a slow image that's really accurate, or we can use fewer spokes to produce each image, which gives us a quick image, but it's also a bit noisy. And remember my rule, you can accelerate as much as you like. If it's noisy, it doesn't matter. Here's another trick we're going to use, though. The center of radial K-space isn't actually undersampled. The points are much closer together in the center, which means if we produced an image from that, it's going to be low spatial resolution, but it's going to be very close to the type of data set we want to produce. So this is our second piece of information. We're going to use the rank constraint, the fact it's low rank from KT faster, and combine it with this low spatial resolution information. All right, now the big question. What do you call a new method? So this is some of the KT faster method. This is our low rank term. This is our data consistency term. We've got a KT, we've got an R for rank. We're going to add the prior information slowly. So spatial prior is controlled by a lambda value, which is how much we care about this central K-space. Add a temporal prior, and so we've got KT, a P, and an R. Katy Perry. What a great name that is for a method. Now I need to test out Katy Perry against the leaders in the field, something Katy Perry is very used to doing. So we've already seen this Katy faster method, and we've already seen that by setting the lambda values to 0, we don't care about the priors. We're going to combine this with another method, we're going to compare this against another method called KT-PSF, which is partially separable functions. And what that does is it assumes you can reconstruct the full time information from that central K-space. So we represent it with a lambda value of infinity. The big question now, and the question with a lot of things, is we've got 2 extra parameters. We've got 2 lambda values, and we don't know what they're going to be. I'm going to give a bit of a spoiler here. I'm going to show how we chose those lambda values in a second, but we did a retrospective undersampling, so we have our true data set, and then we undersampled it, so we've got a comparison of how well our methods do. So we're actually not getting any of the temporal degree of freedom benefit here. We're just seeing how well it reproduces images if we undersample K-space. And the normalized error it produces is smaller than the other 2 methods. This would be a nice place to end, but I've still got 3 minutes, so I'm going to keep you here. And the reason is because I don't care that much about the error. It's nice, but we're working on a spatial temporal method, and I care about how it reconstructs the spatial information, the time-based information, and also the functional information. So this is just a graph of all of lambda space. It actually goes a lot further, but at the edges we have negative infinity and infinity as well. So it's a log graph, so that represents 0 and infinity. So we're really close to our prior on the right-hand side and the bottom. We make it 0 on the left-hand side and the top. And if you're trying to follow along, the Katy faster is in the top right corner. The KT-PSF is in the top left corner. And this was the value we selected for Katy Perry. That will be the same across all of them, and all of these lambda graphs came into how we selected our lambda value. So in case you're wondering why we selected that particular value, we combined all of them together to get our information. Now, how are we actually testing this spatial fidelity? We're doing a canonical correlation to see how well it compares to the spatial subspace, how well it reconstructs the spatial information compared to the ground truth. And as we can see here, this is going component by component for the first 16. I have gone further as well, but this one shows up nice on the graph. And you can see, so Katy Perry seems in this space to do better, but we need temporal and functional information as well. We have spatial. That's 1 down. Let's go on to temporal information. Now, Katy faster, which is in the top right-hand corner, actually does really well here. So we don't need much prior information to reconstruct the temporal subspace. As it happens, it still does slightly better, and again, I've knocked this up, and it seems to do very well, specifically at the temporal subspace. And KT-PSF seems to be struggling a little bit from the reduced central K-space it's using. Final one of these sort of spaces. Go. Functional information. So I compared how well the method's reconstructed. I put it through some feats for a little bit melodic as well. And check the sensitivity, how well it accepts true positives, of how well it correctly identifies pixels we want, and 1 minus specificity, how well it rejects the ones we don't. And again, Katy Perry seems to do better on this, and KT-PSF, it does actually better than you'd expect given the temporal subspace, actually. So that's why we need to check all of these. And again, here's the lambda graph. We have a bit of an odd bar at lambda x is 0, but I think that's just a reconstruct convergence criteria. And again, these are the methods we're doing. So again, we're in the deep red area every time for Katy Perry, which is exactly where we want to be. It aligns between the spatial, the temporal, and the functional information. That's all very well, but that's a graph, so it's a little bit boring. So actually, let's look at some brains. So these are a few reconstructions. The truth is on the right-hand side, and I've zoomed in to what I think is a key area where a lot is happening. And Katy Perry, you can sort of look by yourself, pixel, seems to be doing the best out of those methods. There's also an interesting period on the other side of the brain, which you can look at as well. It's kind of 2 interesting periods in this segments in this finger tapping task. But it seems like my method at this stage, with this data set, does better. Now for the big things. Where do I go from here? I need a bit more of a concrete way to choose the lambda values. I have some ideas about that, but I need to make it a bit more certain. I need to test this on different data sets. And I then, the next stage we're going to do is actually add some coils and see if we can accelerate it a bit further. So my final slide is, remember, acceleration requires knowledge. If you know about stuff about how your data should look, you can accelerate. And the information I'm using is that the center of K-space is more reliable in radial sampling, and the FMRI data is inherently low rank. Thank you to everyone who led to me being on top of this stage right now. Thank you very much.